Спасибо, сказал про отличную мысль.
Дальше не надо, нет вкуса. Что мне нравится вообще?
I was recording nothing. Just I recall you quickly the notation we were using last time, because also your colleague was not in place. So we had said that for the sake of simplicity we assume to be finite or countable. And we call it V. And if you remember, we had just some given, this was given, the probability, so a map P from V to V to 0, 1, which should be just interpreted the probability of jumping to Y when I'm in X, in one step. Okay. So this is just, thus is just positive function with the property that if I sum over Y, the probability of xy, this is 1. So we were just thinking of this as a graph, directed graph, where, okay, the vertices are the points of V, and we put E, so the set of edges, directed edges with positive probability is just a set of our arrows. Be somewhat it can also come back to itself, and so on. So probability of V, you don't need to know any measure theory. Just probability of V, since it's you can think it's finite or countable, is just assigned to every vertex some probability, in such a way that the sum is 1. And then we had considered just the n was the set of paths of length n. So it's just x0, xn, such that the probability of x plus 1 is positive. So it's an admissible path of length n. So we can start here, and this is one element of x4. One step, two steps, three steps, four steps. D is a set of paths of arbitrary length. So not arbitrary, sorry, of infinite length, so paths that never stop. And then we had just constructed at that time, so for each initial probability measure on V, we had constructed, but it was a simple construction, a probability P mu on paths. So this was a probability on the set of paths. So the probability of a path is just like, this is the property that if you fix such that it is identified by this property. If you fix x bar an element of the n, okay, then T mu of all the x in D such that at time 0 I coincide with x naught, at time 1 I coincide with x bar 1. And so on up to n. this is nothing but, so the probability that I start in this bar naught times the probability of going from this point to this point after is really what you expect, is what you expect from the picture in some sense. You start with distribution mu, so you randomly with probability mu of x you select a point x, then you jump every step according to this path. Everybody with this notation, everybody is important. And I don't recall all we discussed last time, but we had discussed briefly, so harmonic functions. Harmonic functions. Basically, with some properties that I'm not going to recall, we say that if we fix some subset of our graph, so this was the original B, we fix some subset of B, and okay, first an harmonic function was just a function of this property on B, and we had basically with some technical assumption we had just discussed that if I fix the value of f outside some subset of B, there is a unique way to extend this function to the interior in such a way that here it's harmonic. And this choice was, it existed and was unique. Okay, if you remember, we had discussed this. Okay. So, what we want to do is to get, at the end, some potential theory, as I said. So these harmonic functions are a first ingredient. We will kind of mix the ingredients a bit later. Today I will speak about a different object, a very standard one, which is invariant measures. You may have heard about them, for instance, in context of dynamical systems. So, and today I want to, so we will define invariant measures. And provide a representation of invariant measures. Well, in the case where there is only one, of this invariant measure. So you see that if you think this as an operator, you give me f, and I make a new function, just summing over y, p of xy. This is, an harmonic function is just a right eigenfunction of this operator, right? So invariant measure will be just left eigenfunction. Okay, let's. Do you have questions up to here? Everybody, are you comfortable with the notation? Yes? So you should speak now, if not. Okay. So, definition, invariant measure can be defined in many different ways. So let's use exactly the dual of that. So a probability measures, let's call it phi. So probability measure on the vertices simply is called invariant. If for all f simply, is the sum for all the y simply sum over all the y So you see, I can think that p acts linearly as an operator to the right on functions, to the left on measures, and this is just an eigenmeasure of this operator with eigenvalue 1. If you give me a measure, phi, I can make a new measure on the x, just by summing all that. Is it clear that, okay, just if mu is a probability in B, then the measure mu p, defined simply by mu p of x, is the sum of a y of p of mu of y, p of y x. So if you define this, then mu pi is a probability. Because if it's positive, it's sum of positive things, and it's a sum over the x. The sum of the x of this is 1, so the sum of the y of this is 1, so it's a new probability. Okay. So invariant just means that it's a left eigenvalue. You see, what does it mean? What does it mean? Mu p. If you have p, sorry, mu this p. That's why it was not readable. Mu p. If I give you the transition probability, mu, you should think that is like the law at which you select point y times 0. Okay. What's the law where you, at which you are? What was the law of the point where you are at time 1? Okay, it's mu p of x. Mu p of x is the probability that your process is in x at time 1 if you start in time 0 with probability mu. Right? Because what's the probability? So mu p of x is just the sum of the starting point of the probability of starting in y times the probability of going on time to x. So it's exactly the probability of being in x after time 1 if you started in y with probability mu. So if you want, we can write it for this fact. Quite simply, an equivalent definition, so the mark P is invariant if and only if when you consider a probability on the whole Markov process started with probability p, if p is equal to x, xn is equal to x, is p of x for all x. Right, because just as we discussed at time 1, if p is invariant, p is equal to Greek pp. So this means that at time 0 I have the same law as at time 1, and then I iterate time 2, time n, and so on. Yeah, because it's like, these happens if and only if, if p, so you iterate this operator n times, is equal to if and for all n, if you know it just for some n, it could not be that. It could be that you are not actually invariant. Okay, so we want to provide a representation, sort of explicit representation of this measure, and it's a quite a curious result and not really intuitive. I mean, what we wrote, I don't know if you're comfortable with the notation, but if you understand the notation, it's very kind of straightforward. But it's quite useful thing in general to have a representation of this. So first, let's say first that if V is, so if our Markov chain is, say, a finite set and is irreducible, there exists a unique invariant measure. This is quite simple to check. So let's say proposition. Let V be finite. And suppose you remember this notation we wrote the other time that x to y means that I can go from x to y just following arrows, right? For every single y. So this proper, so from each x, I can go infinitely many steps to y, following following a path of finite length and positive probability. So this is called sometimes irreducible chain. Because if you do not have this property, you can reduce it to chains that have it. Then, let's prove just uniqueness, because we will give a representation of existence of the invariant measure. We will prove it in some sense through explicit formula. But then, so there exists at most one invariant measure. So that's like, the eigenvalue 1 of this operator is simple. There is only one thing. The proof is quite quick, so we can go to another. So, if P is invariant, then, of course, P of X is the sum of Y of P of Y, P of X, which implies that P of X is strictly positive for X due to irreducibility. Because this is, suppose that P of X is 0 for a given X, okay? Then this formula tells me that P of Y must be 0 on all the Y that have an arrow going from Y to X. Okay? If P of X is 0, then if P of X is 0, since this is a sum of positive terms, all the Y that have one arrow going to X must also have P of Y equal to 0, because otherwise there will be one positive term in this sum. So all the Y from which I can go in one step to X are also 0, pi is also 0 there. So also, the pre-images of these, all the Y's from which I can go in two steps to P of X must be 0, and so on and so forth. And since from every Y I can reach this point X, because this was true for both X and Y, P of X must be 0 everywhere. Okay? If P of X equals 0 for some X, then P is identically 0, so it cannot be a probability. An invariant measure which has one, if the Markov chain is irreducible, an invariant measure, which has this property is just the 0 measure. If one is 0, all the ones that go to X are 0. Since okay, by reducibility it's 0. Now, so this immediately gives us uniqueness because, you see, just by standard convexity argument. So we took V finite, right? So V is finite. So P of V is just a simplex. Really, you can think of if V as an element is a simplex in Rn. D element is a simplex in Rd. So it's D and embedded in Rd. So invariant measures are closed by convex combination. This means that if P and P prime are invariant, then alpha P plus 1 minus alpha P prime is invariant. So this is, it is like, you are like a triangle, and you are taking some convex, some linear convex subset of it. So since this property was true on the simplex, invariant measure as just the closed convex hull of the extremal invariant measure. So, is it okay what the word I used? Extremal means that you cannot write it in this way if not with alpha equals 0 or 1 or p equal to p prime. If you want, I detail more, but maybe you already heard these things, and I know you are taking the class on Markov chain, so probably you have seen this theorem already. So this implies that okay, and this implies that extremal invariant measures. This is true in full generality. Measures are mutually singular. This means that mutually singular, so if P and P prime are invariant, but cannot be written non-trivially. And say P equal to alpha mu plus 1 minus alpha mu with this invariant. So invariant and extreme. So this means extremal, okay? This means extremal. So you have two invariant measures that are extremal. Then they must be mutually singular. Why? Because this was the point. Because otherwise, suppose that P of x is, say, strictly bigger than some P of x prime, which is non-zero. Okay. So suppose that they can be, when one is 0, the other is, there is a point where they both are non-zero. Okay. Then you just take alpha. So there exists x. Sorry, the prime was here. There exists x such that you just take alpha p prime of x and p of x. Okay. And you take mu as p prime of x, and mu of x, so mu of x, mu of x as p of, sorry, mu of y. As the difference of y minus I come to this. I want to tell you that the extremal invariant measure are mutually singular. Okay, because are you following? So I have my invariant measures. They are a simplex themselves. Okay. Okay, they are like a triangle of a smaller dimension and two dimensions. Now, I know that each of them must be positive everywhere. So two measures cannot be mutually singular. Cannot give one, right? It's not like this is concentrated on one set and another invariant measure is concentrated on another set. Okay, they must be absolutely continuous, one with respect to the other. And I want to say that this cannot happen for extremal measures. So since the whole set of invariant measure was just the convex hull of the extremal one, if there is only one extremal measure, there is only one invariant measure. Okay, so I want to just say that the extremal invariant measure are mutually singular, and so this is true because if they are not mutually singular, yes, okay, if indeed, if they are not mutually singular, you can check that then I can write P, so P prime are invariant, extremal, and not mutually singular, okay? This means that I can write P as alpha P prime, that's a rho P prime, plus, let's call it P second, plus P second. Okay. So, this is the part of pi which is absolutely continuous with respect to P prime, and this is singular with respect to P prime. I'm using too much measure theory? For you, I'm sure I am, but it's just a parenthesis. So, once we quit it, you can get back to that statement. And you can check that this part and this part must be, this is a measure, not a probability, but they are invariant themselves. Okay, so if you can write it as P second of V divided by P second of V. This is a probability, and I wrote it as a convex combination of invariant measures. So since I know that they are positive everywhere, there is only one extremal invariant measure, so there is only one invariant measure. Okay, this fact is actually true even, that invariant measure is mutually singular, it's always true. If you have an evolution semigroup, irreducibility or not, it will be always true. Irreducibility tells us that invariant measures are positive everywhere, so they cannot be mutually singular. So what I want to discuss today is explicit representation of the invariant measure. So this is, I mean, I don't know if you see a bit the problem, but typically it's quite intuitive, I think, that if I give you something like this finite, there is only one way, maybe to put weights here, so that when you shift the weights with this function p of xy, the weight in x goes with, what is an invariant measure? I put here on this point some weight, here on this point some weight, here on this point some weight, and here on this point some weight, right? The sum is, say, 1. Okay? And then I have, on each arrow, I have some probability, so I have also some sort of fractional weight that I transfer at each step. So the weight that is here, say that probability, I don't know, was 1/3 here and 2/3 along this arrow. The weight that is here at the first step, I put 1/3 of the weight here and 1/3 of the weight here. From here, I do the same along XR. Okay, here there is only one. I put all P of X prime. I put it all here. And the way that was here, I split it according to this weight of these two R, one here, a bit here, and so on. The invariant measure is the one for which at the end of the procedure, the weights are the same as the one I started with. Okay? It is not something random. It's some, okay, is an eigenvalue of this operator. If you think on a finite graph, this is, Pxy is really a matrix I mean, if V has D entries, it's a matrix D times D, right? So I'm looking explicitly, I mean, there is no reason why I can write kind of explicitly the left eigenvalue, the left eigenvector of this matrix, okay? But for the fact that the sum is of the Y is 1, so on each column the sum is 1, okay? And we will give a combinatorial representation. And this is very not intuitive and quite surprising, at least for me, it's not intuitive. Why this representation works. So, so let's give a definition. This explicit representation will come useful later to calculate some explicit limit. Definition. So the root of the tree is a graph. Is a graph. Is a couple actually. So X, where tau is the graph, X is a vertex in tau. Okay, I identify here the graph with its vertices in this diagram. X is a vertex. And for each y in tau, there exists a unique path, okay? There exists unique n and e in dm of tau, so a path of length in tau, such that x0 is y, xn is x, xi is different from xj, for all I different from j. And so this means that xi plus 1 are edges in tau. So what is it? We understand it very quickly, because the definition looks bizarre. So it's just a tree with a marked vertex, okay? Directed tree, a graph with directed. I have a graph, and there is a special point marked. The root is called the root of the graph. The root, как по-русски, понимаете, root?
Корневое дерево, видимо. Ну, корень. Корневое дерево.
Да. So this is x. And then for each vertex, well, including x, there is a unique path that goes to x. So for instance, from here I can only go through here. I mean, it's unique if I impose that I never come back, of course. But, okay. Well, actually there is no need of this. This condition is if I put uniqueness, it's not necessary. Okay, so you see that according to this definition, what should happen? For each y, there is one and only one arrow that exits from y. Because if there would be two, then I would have, the point I reach from y to the first arrow also is connected to x, so I would have two paths, two distinct paths that would connect me to x, and the path must be unique. And so some y could receive more than one arrow, but only one exit. And then if I follow all the arrows that exit at each step, I finish in this point x. And okay, the path from x is trivial, it's just x not equal to x. And from x, there exit no arrows, because if there would be an arrow, then well, I could kind of, it would not be a tree, I would have a loop again. So I would have, this is not here, right? So I would have more than one path. Okay. So that it's exactly this. I could have many paths. It's exactly this figure. Okay. So it is a directed graph, which is a tree even if you look at it in a non-directed way. But there is a special point mark, which is the root. Okay. So with some abuse of notation, sometimes I will write this R of tau as it's like the root of tau. It's a couple, but I kind of write it just tau and its vertex. Okay. So what we want to do, so another definition is, now given V finite, the rooted spanning tree on V is a subgraph of V a rooted tree and as V as a set of vertices. So if I give you a graph with a lot of arrows. And this graph must be reducible, otherwise it could maybe that you cannot look. No, well, I mean, this is general definition. That is non-trivial. Then, what is a rooted spanning tree? Is a subgraph. So this means that the vertices are just all the vertices in V. So I can only remove arrows. Okay. It's a subgraph, but sub not because vertices are a subset of the vertices. The vertices are just the same. Just have to remove arrows. So what do? I choose some root, say this one, so this is my root, this is what. So this was V, okay? Then I choose tau, let's say I do it in blue. This is the root of tau, okay? Our point is. And then I start to remove arrows. So for instance, I don't know, to make a spanning tree, I keep this one, I keep this one, I remove this one. Say I remove this one, for instance, I keep this one, I remove that one. This, so I remove this and this, and I finish it. Okay, what I obtain is a spanning tree. See, from every point I can go here, and they will just one path. Okay, so it's a subgraph in the sense that it's I removed arrows. Okay. Now I want to do a bit of The combinatorics of this is clear. You look puzzled, no? So what I have in mind is the following construction. I start with a Markov chain on this simple graph V, and I make a much bigger graph whose vertices are the spanning trees of V. Right? So let's give some names. So let's call it theta. So given V, finite. Theta, let's say, is the set of spanning trees, rooted spanning trees on V, and let's call, so this is big theta, capital theta, and let's call capital theta x, the set of tau in theta, such that the root of tau is equal to x. So these are all the spanning trees, and these are the ones where the point that I mark is exactly x. Now I had a structure of graph on V, and also weights on the arc, so a Markov chain on V. I want to make a Markov chain on theta. Why so? Because things will be explicit on theta and not very explicit on V. Okay. So this, I had say, this graph original, the white one, and now I have a much bigger graph, typically, where this is a new graph, this is theta, it will have many squares. Okay. Each of them is a spanning tree. Different one, of course, yeah. And so on. Okay, it's pointless to draw in everything, and then I have to build the arrows on here, okay? How do I do it?
So I will be building a graph which such that every vertex consists of the spanning trees of the first graph. So like you would like to consider a bigger graph such that every vertex consists of the
a subgraph, yes.
Okay.
Yes?
Yes.
So well, typically is bigger, but it could also be smaller. I mean, if V was already a spanning tree, then theta is just one element, If V was already a tree itself, then but typically, say for a graph we have in mind which is irreducible, theta will be much bigger. So theta is a set of spanning trees on V. Okay? I just want to define, and then a map. I want to define. I want to define a map Q from theta times theta to 0, 1 with sum over theta tau prime and theta of Q of tau prime equal to 1. Okay? And this, must depend in a suitable way, which I give you. Depends. So Q depends on the P of xy on the P on P times V 0, 1. We have our data, which is V and P. Okay? We want to make a transition probability on spanning trees. And why? Because we will be able to write explicitly an invariant measure here. Okay. So let's define. in theta and y in v, gamma y of tau, which will be a 3 rooted at y, as follows. It's sort of combinatorial procedure. We have the spanning tree tau, so it's rooted at this point here, which is the root of tau, and we fix some other point y, okay, here, and we obtain a new spanning tree gamma y of tau. Now we write it explicitly, but let's make a picture. In what they differ? You see, there is a unique path connecting y to the root of tau. I remove the last arrow, so here there was an arrow, I remove it, and I add an arrow from the root of tau to y. Okay? So the claim is that this is a spanning tree rooted at y. Let's write it as follows. So first let's add to tau the edge root of tau y. Okay, and 2 we remove from tau the last edge of the unique path from y to the root of tau. So the claim is that gamma y of tau is in theta y. Why? Let's check why. Well, first it has no, sorry, not what did I do? So the first, not the last. The first. Otherwise, will not be rooted. The first edge of the unique path of y from. Okay. So, of course, the vertices are exactly the same as the vertices of tau by definition. So it's a spanning. It's a root. So just to check that it's rooted at y. So that from each point there is a unique path going from that point to y. Okay. So the points of tau I can sort of divide them into two classes. The vertices that tau. I knew that from tau I can go to x through a path. Unique path actually. So you can divide the vertices of tau in two classes. Those that go to x, go to the root of tau, passed through y, and those that didn't pass through y. Okay? If they did pass through y, like this point, of course, they have a path going to y, just the same as before. But now this path is stopped here, there is no arrow coming, but it's not a problem, they go to y. If they were instead going to x, go to the root of tau without passing through y, then the path is just the same as before with this arrow added. So I got a new spanning tree, just I changed the root. It's plain. I define, so then I define a Q in this way, Q of tau prime is equal to P So P is the one given, and P is on V, and Q is on tau. P is on the vertex of V, and Q is on theta, is on spanning trees. Okay. So this is P of the root of tau, the root of tau prime, if tau prime is equal to gamma root of tau prime of tau, and 0 otherwise. So what am I doing? I have my original graph with a lot of arrows, okay? But now I am in the spanning tree, and now I'm running Markov chain on spanning trees. Let's do this. So this is tau, is root that is root, okay? Where can I make a transition? To what new spanning tree can I make a transition? So, all the transitions that are allowed are those done by that procedure described there, which means, like, but are those obtained by that procedure where the blue arrow was an arrow of positive probability in the original graph. So I look at the root of tau. In the original graph, there were many arrows coming out from the root of tau. I don't know, for instance, there was this, there was this, there was this, and so on. So if in the original graph, these three transitions were allowed from this point, in this graph on spanning trees, there are three transitions also allowed that are I add this arrow and remove this, or this or this, that's the answer. Or I don't know, I add this arrow and remove this. So each of them is a transition to a new spanning tree. Or I add this arrow and remove this. Okay, so how many transitions, how many arrows there are from the spanning tree tau? As many arrows as in the original graph there were in the root of tau. And the probabilities that you put on these three transitions are the same, but before you went to a point x to a point of y of the original graph, now I go from a spanning tree to a new spanning tree following this procedure. It's a bit, you have a graph, you made another graph, whose vertices are defined as a subgraph of the old graph, but it's nothing more than that. Can I go further? If you have a doubt, you can, like, want me to start again the whole construction on the spanning trees, you just tell me. Have you seen this construction? You have not seen. Okay, Bushietov didn't speak about it. And, okay, so this is how it's defined. We want to define this map. And now, so why we did it for the following reason. So I don't know if we can call it. Let's call it theorem, even if it's it's simple, but it's kind of relevant for us. Define let's call it W. W from theta to as W of tau is the product on all the edges in tau applicable xy, here is P of xy. Then sum of tau of W of tau Q of tau prime is equal to W of tau. So we'll say that W is not is actually yeah, is implied. So you see here we found explicitly less eigenvalue of the operator Q. On the space is much more messy than the space of just probability measures on V, because these are like measures on spanning trees on V. But we found explicitly one of them. And then we will see how we will use it to find the... sorry, I defined W, and assume that V, V irreducible. Irreducible. This is the equation of invariance on theta, right? So we have to check. Product of all the edges in times Q of tau prime equal to you see why this could be true, say. Why these two quantities look pretty much like one each other? Because you see, the product of all the edges in tau, if Q of tau prime is strictly positive, so in this sum, there will be a lot of zeros. But whenever Q tau prime is positive, this means that tau prime was obtained by tau through that procedure. So all the edges are the same, but erased one and added one. The procedure of just add something, remove something. So this product here is the same as this product here, but there is one factor missing and one factor added. Okay, that's so to prove the equality, we just need to check what is missing and what we add. I don't know what is actually. Maybe I keep it. So these I can write it as just the product, all the other. I just take out this factor, which is on the left hand side, and then sum. So let's write it smaller. simple edge is in tau prime of the probability of the edge times the sum of rho tau times theta of the product just multiplied and divided by this simple factor, and then Q of tau prime, I write it by the definition, so it's probability of root of tau prime times, I mean this is just 1 or 0, tau prime is equal to gamma root of tau prime of tau. So I wrote the left hand side here. I put this in factor just because it is what is on the left hand side. Then it's sum over all the tau and theta. There was this, I divide by this, which is here. So this. Then there is Q of tau prime. I just wrote explicitly what it is. This is the probability ongoing from the root of tau to the root of tau prime. And then there is an indicator of tau prime is gamma R of tau prime of tau. I just copied the definition of Q of tau prime. Is it this is just one indicator function of the so K is W of tau prime, okay, it's here, W of tau prime, sum over all the tau and theta, same, I have to sum this. And now, what I just said, who is this ratio? So, since on all the terms that are non-zero, there are only, here there is one factor, I mean, they only differ by a factor. This one here is obtained by this one here by removing one and adding one edge in the product. So, what extra edge did I remove? And then there is what extra edge did I add in tau prime is very simple. It's exactly root of tau prime. Was the blue arrow that was in the graph that I had to erase here. So here, the extra edge which is here is just root of tau prime. And what was more, what was extra in the numerator instead, you remember was the first edge going out from y, so the root of tau prime, in the graph tau. Okay? So here in the numerator there was probability of root of tau prime times 2 kind of the first, the only edge going out in the tree tau from the root of tau prime. Let's call it x tau prime. So x tau prime is the first edge in the tree tau coming out from the root of tau prime. Okay. X tau prime. First, so the only, it's unique, is the edge, unique edge out of root of tau prime in tau. This is x tau. No, the edge is sorry, that's root of tau. This is what I had to remove in this top product in the numerator here. Okay, but now these just go out. Okay. And if you think for a moment, so what I'm left, let me first write the formula, and let's check. So here I sum just over all the y in v of p of root of tau prime 1. So what I'm saying is that what I'm saying is that in this sum over tau, okay, all the terms that are non-zero, so for which tau prime is gamma of tau prime of tau, there is, in all this sum, there is exactly one term which is non-zero for all the vertices that are in V that are reachable from tau prime. So let's try to check this. So I had a spanning tree rooted somewhere at root of tau prime. I'm summing on all the on all the trees that through my procedure gamma will finish to tau prime, not those that can go to tau prime. I mean, I'm going to tau prime equal to gamma of rho tau prime of tau. So I'm summing the probability of the root of tau prime and some point, but I'm summing all the tau that will finish to tau prime. So I have tau prime. Okay, so is something like this. And in the original graph, there were some arrows. Blue are from the original graph. And what I'm claiming is that for each of these arrows, okay, I find some spanning tree that will, bijectively, I find bijectively a spanning tree that will finish in tau prime. Okay. How do I do this? So let's say that we take, for instance, this blue arrow, okay? We want to find a spanning tree tau such that when we apply the procedure gamma, we finish in tau prime. So it's the reverse problem. Well, this time, so let's say that I fixed one blue arrow. What I take as tau, bijectively on this, is just the spanning tree obtained from tau when I indeed add the blue arrow and remove the last edge in the path going from the edge of the arrow to the root of tau prime. This arrow will have, this tree will have a positive probability, so it will count and this will count. It will have a positive probability on going to gamma of r of tau prime tau, because from this vertex, which is the root of my tau, there will be in the original graph an arrow that goes to the root of tau, and so through gamma, I add this and remove this, and we'll finish exactly in tau prime. Okay? So I'm solving the inverse problem now. You give me an arrow that exists in the original graph, and I want to find the spanning tree tau that is mapped through this procedure gamma, remove one edge of one edge, to tau prime. And how to find this tau is quite simple. You just add the blue arrow to tau prime and remove the last edge going from this point to the root of tau prime and tau prime. Okay. So we have this fact, but you see that now in the original graph we knew that for every x the sum of the y of p x y is 1. So all this sum is just 1, and we have got w of tau prime. So I must admit that the algebra works quite fine, but I'm not able to give you any sort of intuitive fact quickly to why we should kind of lift everything up to this space of spanning trees. But as a corollary of this fact, now we get a representation of an invariant measure on the original graph. So, corollary of this theorem on V, define P of X as the sum of all the spanning trees in theta x of the weight of the spanning tree. Okay, so this just means sum of root tau theta. So root I sum, to calculate P in x, I sum the weight, this probabilities here, that with these measures here, W of tau, over all the tau's root at the point x. Okay, so this is just product of all the tau x, y in V times V of the probability of x, y, if we want to write it in the original P x, y. Then P okay, I have to divide it by normalization constant. Z is just the sum over all the x of this, so it's the sum over all, is it just a number? Is the sum over all the tau in theta of W of tau. Then P is an invariant, is the invariant. The invariant probability on B. So if you want, you give me a matrix D by D with these entries. I just know that the sum on each row is 1, and this expression gives you an eigenvector of the matrix. You can just think of it as a linear algebra formula. Okay. Which indeed is just some Kirchhoff principle in linear algebra. So why this? So So we had the invariant measure, okay, on this bigger space. And in general, you know, if I have some graph with a mark, so I have if we have theta, okay, we have V, and we have to map R from theta to V. Okay. In general, if I have a Markov chain here, and I just apply R, I will not get a Markov chain here. So suppose that here I have some Q of tau and tau prime. Okay. And then here I could make some, I don't know how we can call it, Yn, like our paths on the space theta. Okay. They came with a probability measure Q, that was the probability measure on paths on theta. In general, if I take as R whatever maps, it will not be true that xm equal to R of Yn as low P. So in other words, if I just take a function of a Markov, if R is whatever, not the root, but whatever, it's not true that the map of a Markov chain here will give me a Markov chain here. But our rays, Q tau tau prime, had a very special, if I take here now the root instead, what I'm claiming is that these will have exactly the law of the Markov chain we have on B. Why? We will write it, but this probability Q tau tau prime had a very special probability, a very special property that just depended on the root. So suppose what I'm saying, we had, I'm here, we had this, okay, let's do it. We had this Markov chain on where the space is spanning tree. Each of them is some spanning tree. And now I observe my Markov chain, okay. I know everything. I know really what's happening on this space of trees, okay. So this can go here, 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 but I really observe what happens. I really observe what happens, okay. And I know that I start here, then I go here, then I go here, then I go here, and so on and so forth. But he only knows the root of where I am. He doesn't know the whole thing. I only inform him at every step. The root was X, now the root is Y, now the root is Z, and so on. So I know everything. I know the whole information, and he only knows R of what I know, only the root, okay? What does he see? What does he see? He sees exactly a Markov chain. He sees exactly some paths. He sees exactly this was V, I don't know. This was V and this was theta. This is much, much bigger. And so I see things here, he only sees R of what I see. So the random walk, the walk that he sees is just, you know, you start in R of what I saw, and then you jump on the various roots. But due to the properties of Q, what is the probability that he sees the transition from here to here is exactly the probability that I had a transition from a tree rooted here to a tree rooted from a tree to a tree rooted here. And this only depended on, and this in my original graph, this was exactly Pxy. So if I'm in X, if I know that, so I am in some tree tau, okay? Your colleague, he only knows that I'm in root of tau. So he only knows X, only knows the root of my tree. He only knows the blue point. He only knows the blue point. Each of them had a marker point, and that's the only thing he knows, only the marker point. So what does he see? Once I'm in X, okay, what that he sees is exactly a jump to a point y, with what probability? With probability that from the tree tau, okay, I go to a tree rooted in y. But by the way we constructed Q tau tau prime, this was exactly P of xy. So let's see, let me write it better. Let's write it precisely with more time to do. So remember, so let's make it slightly more formal what we just said. So R was this map from the tree to our original graph, that was the root. Okay? And we can lift it. We can lift R to a map. Let's call it capital R from parts on theta to parts on V. Okay? Simply R of a part here, let's call it Y, and is just R or Y. And all the paths, and this is the position N, and what he knows is just the root at the position N. Okay. So R of Y is a path in V, which is at time N is in the root of Y. And then, so if, say, QP is, this was the probability measures on path on theta, okay, with associated with Q. So this is just the probability measure that I made on theta on the big graph, starting with probability, W. W over is constant, W were the weights, okay? I start with W on the big graph, and then I make probabilities on paths giving this rate. So the probability of a path is, I start in some tree with probability W of tau, then I make the first step with probability Q of tau tau prime, and so on and so forth. Okay? So what we just discussed is that then the push forward of QW through R is P. Then QW composed with R to the minus 1 is P with initial measure phi. So this just means this is a push forward, so this means that P pi of a set of paths, okay, for instance, I don't know, the first step is here, the second state, okay, is Q, started with that measure, of all the y, such that R of y are in it. Or, if you want, written more precisely, written more explicitly, or it's just a push forward, but I'm sure. The probability, so this was the probability on V built starting with in probability pi that was written here, and then making the transition with P of xy. Okay? This was our probability. So the probability of all the paths such that x0 is in x, x1 is in x1, xn is in some given xn, okay? This is the same thing of the probability on theta, on path on theta, started with W, of all the y on theta, such that the root of y0 is x, the root of y1 is x1, etc., etc. This is what we were discussing. Why? That's exactly what we just discussed, is that, I know this, this is the probability, according to me, that knows all what happens on the big graph, okay? And as you remember, he only sees the root. So the probability that I see, so the probability that he sees, I don't know, jump from x to y, and then from y to z, okay? What is this probability? It's the probability that in the original graph, I made a jump from here that had root x to a tree rooted in y, and then from a tree rooted in y to some tree rooted in z, okay? But this probability is exactly, by the way I built q tau prime, is exactly p of xy times p of yz. Because from a tree rooted in x, I jump to a tree rooted in y exactly with probability p of xy. Because I removed an edge, I added from x the edge from x to y exactly with probability p of xy. It's the way we constructed q tau prime. So I said again, in general, if you have a map from one graph to another, it will not even map a Markov probability to some Markov probability. But in this case, it does, and the map through R is pushed forward to R, is exactly our original Markov probability P. Okay. So in particular, if this was invariant here, so the law of y0 here was equal to the law of y prime equal to law n, the same happens here. Okay, so this is the proof of the corollary. It's just the fact that mapping from the tree to the root associates to our big Markov chain our original Markov chain. Okay, so we got, for me this is very far from being kind of easily, to give an easy intuition of it, so that the invariant measure, so you have a Markov chain on a finite graph, it's irreducible, it's quite expectable that there is one invariant measure. It's like, this is like a ergodic theorem. It's just, you can go from everywhere to everywhere, it's some ergodicity. But then here we have an explicit representation, and this is not intuitive, so this is the sum, at least to me, over all the spanning trees rooted at x of the product on the edges in tau of the probability edge. So like you have some complicated graph which makes many jumps, many possible jumps. I want to calculate what's the invariant measure here. Okay. So the invariant measure describes the long-time behavior of our chain. Like if you wait long enough, in some suitable sense, you will be close to the invariant measure. And how do you calculate it? Well, you start from this point. You calculate all the many spanning trees that have a root in this point, and make the product of the probability of spanning trees and sum. It's a bit of a, okay, it's not intuitive, I think, in general, but it's true. Okay. So this will be, so the invariant measure will be one of the ingredients of our future development. We are, it's a good to stop here. So maybe you have not seen much measure theory yet. but this is, all these things are sort, because the space of paths is not finite, but it's kind of, for many, these things you can just kind of write it in a finite way, so it's quite